Hi, I'm Mostafa from Biomediq company and University College London and University of Copenhagen, working on dementia modeling as researcher and PhD fellow. It's my pleasure to give presentation on my work about recurrent neural networks for disease propagation modeling using an incomplete data. So here is an overview. I will briefly talk on, give a talk on introduction to disease progression modeling and Alzheimer's disease and biomarkers, MRI biomarkers, and we'll go through the background on handling missing data. Then I will shortly explain long short-term memories and we'll start to explain our proposed method based on for robust training of recurrent neural networks. Then I will explain the dataset briefly and experimental setup, and we'll show the results of modeling and diagnosis. And finally, we'll conclude this presentation. So, this is progression modeling can provide better tools and applications to monitor and to diagnosis of disease for clinicians. Using longitudinal data. I will focus on Alzheimer's disease, which is a neurodegenerative disease disorder. And actually, early diagnosis of this disease is very challenging, and it is usually made once cognitive impairment has compromised daily living. As you can see here, this is early disease which affected learning, thinking, and planning, but it's not easy to make a difference that it is normal aging or Alzheimer's disease or different types of disease in the early disease. So we use magnetic resonance imaging biomarkers because MRI is the best non-invasive way to actually examine changes in the course of AD. Of course, there are some other types of biomarkers, but none of them are in, none of, for example, pathological biomarkers are non-invasive. We will focus on volumetric analysis, which is widely used as an ROI-based biomarkers to demonstrate the atrophy in the brain. As you can see, by advancing the disease, the brain starts to shrinkage, and this is the whole brain shrinkage, which is easily seen here. And also, you can see that hippocampus also starts to shrink, and ventricle starts to enlarge while the disease progresses. Well, we are going to use disease progression modeling using RNNs. Actually, existing disease progression modeling algorithms neglect temporal dependencies among biomarker measurements. They make some assumptions about the trajectory of these biomarkers, and most of them do not model multiple biomarkers together. The robust training of RNNs are necessary because longitudinal cohorts contain incomplete data, and which hinders the application of basic RNNs here. But we will focus on LSTM network because it can deal with exploding and vanishing gradients. As you can see over the course of time, the initial values, the network begins to forget the initial values of input, and LSTMs are going to deal with this problem. In the context of handling missing data in RNNs, there are a few methods. One of the most widely used techniques are pre-processing techniques, which are going to use two-step algorithms like imputation or interpolation based on mean, forward selection, expectation maximization, or even cube or spline interpolation. For example, this is an example of forward selection that it uses the previous stage or previous available value to fill the blanks. So the performance of these methods are highly influenced by the method of data imputation or interpolation. On the other hand, we have some masking methods that try to actually handle the missing data by adding some new parameters to the network, like here and here, and take the advantage of the patterns of missing data to learn the parameters. So they use these possible correlations between the learned data and test patterns to handle the missing data points. Of course, there are some padding methods. For example, if there are some missing data in the beginning or at the end of the time points, we can throw them out, and this is another method that can be used for handling missing data. But we propose a method, a built-in handling of incomplete data based on a generalized formulation of backpropagation through time. So, assume this is a basic vanilla LSTM that uses 3 reset gates, forget gate, input gate, and output gate with a modulation gate to learn how to forget or how to remember the memories during the time. And this is the cell state. So we start to feed forward through the time based on the gate observation, and to reach the output of the cell over here, which is our recurrent value or hidden output in the LSTM. After feed forwarding, we start with back propagation. So we need to actually compare the actual value and estimated value in the output that we found through feed forward. Here we deliberately define actually taking a batch-based backpropagation through time, which is taking the average over all available samples and time points, and then just take the derivative of this loss function to find the derivative of this loss function with respect to the weight. We backpropagate over time, and finally we find the partial derivative of loss function with respect to the weight. For simplicity, assume this is an unfolded RNN that can be defined also based on LSTM, but with some modifications on forget gate and some other reset gates. This is input gate with n inputs and 3 consecutive time points. This is hidden layer, and finally this is output layer with 2, for example, m, which is 2 output nodes. Assume we have some missing points. We define 2 normalization factors here to weight the loss function later on. One of them is based on per node input normalization factor. For example, we have 1 out of 3 here available points, or we have completely 5 over 9 time points available here for normalizing the input factor. And if we have some missing values in the output layer, we can define, for example, 1 over 3 available time points as a normalization factor for the output layer here. Afterwards, we add these normalization factors, plugging them to the loss function to somehow weighting the loss function through for backpropagation through time, which is shown here. This one is y, could be, for example, an m by n by t matrix, and we are taking into account the number of available points feed forwarded using the input and backpropagating through the available points in the output. We do the same backpropagation procedure. And finally, for finding the gradients of loss function with respect to the weight, we add the other available normalization factor for weighting based on the input in the chain rule calculation in the output. So we use actually this method for modeling the progression of AD using Tadpole data challenge, which itself uses 3 phases of ADNI, 1, go, and 3. The biomarkers are extracted from over 1,700 subjects between 2003 and 2017. The third phase of this ADNI is ongoing in the procedure. And it is partly actually labeled to 3 labels. And we use T1 weighted brain MRI biomarkers, and they are extracted using the FreeSurfer tool. We use the volumes of ventricles, hippocampus, whole brain, fusiform, middle temporal gyrus, and interhinal cortex. We use 11 visits, including the baseline, with a fixed interval of 1 year. Out of these many subjects, over 700 subjects with having at least 3 time points, 2 for ensuring the training or feed forward, and 1 for additional for backpropagation are selected. And finally, the dataset is partitioned to 3 non-overlapping subsets based on training, validation, and test. We use a momentum-based batch gradient descent method to optimize the weights. People connections are used to improve the performance. Network weights are initialized at smaller ranges. And also batch size is set to the number of available points, which is 742. We use visits 1 through 10 to estimate the visits 2 through 11, and validation set is used to tune the optimization parameters to achieve the lowest mean absolute error. These are the results of results for modeling performance, which are mean absolute errors per biomarker using our method and 3 other methods. 2 imputation-based methods alongside LSTM network, and also 1 state-of-the-art regression-based. This is progression modeling. Here you can see that our results outperforms other methods based on MAEs. We use the estimated biomarker measurements to train a linear discriminant analysis classifier to find the posterior probability scores. We use these scores later on to find area under the curves. And these are the results of AUCs for the aforementioned methods, which is this one is multi-class AUC. As you can see, also in classification performance, our method also outperforms other techniques. And the results of our method are comparable with those of the cat dementia channels challenge, which were the top 5 were between 0.75 to 0.79. To see how significant are the improvements, we used two series of tests based on modeling, absolute error and classification accuracies. As you can see, our results are mostly significant than other techniques for both modeling and also classification, except for this one. Finally, to see robustness against missing values, we started to randomly removing up to 50% of the available training data per biomarker. Just note that we already have missing values per biomarker. As you can see, 2,000 out of 6,000 are available per biomarkers. So we start from this point to up to 50% of this many biomarkers. And these are the results of the robustness. As you can see, up to 31%, our method works better than other techniques. Afterwards, LSTM with forward selection outperforms our method. Finally, a generalization of backpropagation through time is proposed for RNNs, aiming to improve their robustness against missing data. It is, of course, applicable for other types of RNNs. We applied for all LSTMs. We can use for GRUs, for example. It is applied for AD progression modeling using volumetric MRI biomarkers of ADNI. To the best of our knowledge, this was the first time RNNs have been studied on neurodegenerative disease progression modeling, and the proposed training method demonstrated better modeling and diagnostic performance than both imputation-based and regression-based methods. And the results of classification are comparable to those of the cat dementia challenge. I want to thank the EU, UCL, KU, and Biomediq for their support, and my supervisors from University College London and University of Copenhagen, and my colleagues from Biomediq company. Thank you for your attention. You are welcome to ask if you have any questions. Yes?
Hi, thanks for your interesting presentation. I have both an invitation for you and a question. So first, the invitation is about the Cat Dementia Challenge. As you may know, it's still open, so I welcome you very much to submit this new method to the challenge as well, to really compare it to the already existing results. And a question about your method. As I understand correctly, all the data you use now is from within 1 year, right? You only use...
No, actually the data is obtained over 20 years. The time intervals are 1 year. For example, we select time points per year.
Oh, okay, so now I understand it. Okay.
Now we are working actually for unfixed intervals. So we are doing experiments on that, not fixed to 1 year, so we can have some few months.
And do you do any alignments of subjects, or you just align them at baseline?
There is no alignment in our method.
Okay, thank you.
You're welcome.
Okay, then I have a related question, or maybe it's related. When you mentioned that your batch size is set to the number of subjects, I wondered whether you took the stochastics out of stochastic gradient descent, but apparently I'm not familiar with the data set. You only take part of the timeline.
Okay, let me explain. Actually, this is to benefit from all the available subjects or observations and time points and measurements to see at least at one point they can touch one of the nodes per biomarker, per observation, per biomarker, and per time point. So we want to take into account all of these measurements, but you can do that with mini batch or smaller than this many, because the number of subjects are not that much, so they were like 742 subjects. We use all of these subjects to train our network, but you can use a subgroup of these subjects. But for stochastic gradient descent, you have to select one, for example, subject. If it has, for example, missing data, it cannot be incorporated during the training. So we are going to use all these subjects to take into account and as much as possible the subjects for calculating errors during backpropagation.
Okay, I think then it's no longer stochastic gradient descent, but
no, it's
gradient descent
it's not.
With your update rule. Okay, I understand. Thank you.
Yeah, thank you for the interesting talk. Just have one question. When you so as far as I understand, you just downweight the missing data points, but you don't so you don't remove them somehow completely.
No, we don't remove them. We actually take into account all these missing data points, but just weight them, weight the input and output based on the number of available points.
But
so
this means you have to fill in some value for the missing data point, even though you weight it down, so you have to put in a 0 or something. What do you input
for simply, we say this is 0, so that, for example, during the functions, they are unfired, actually.
Unfired?
I mean, the activation functions are, we can assume that they are unfired. When we set them to 0, 0 can be the mean of the values. I mean, the mean, for example, the values of activation functions are between -1 and 1 because we use tangent hyperbolic function. So we take 0 for saying that these values are not available.
But have you tried to just have a kind of a mask, so which then disconnects completely these values
No,
from
we
the loss?
don't. Actually, we don't use masking because in the masking method, you are to learn the position of this
for the ground truth. Because I understood that you also for the ground truth for training. You just downweight the.
Can I go to the slide?
If you go to the slide. The formula, no, back. Yes, there.
Okay.
Yeah, so the why, the formula, if you leave the formula.
So
the next slide. No, it was on.
It's not my problem. It's
okay. Yeah. Well, maybe we can discuss this offline. So, but there was still the. Oh. Okay, now we are far out.
I do nothing, I swear.
Okay, yeah, let's discuss it offline. Yeah, thank you.
Can I have one final question? I'm really curious. On one of the last slides, you showed that if you remove many more data points, that LSTM with forward imputation takes over. Yeah. Do you have an intuitive explanation for that?
Actually, forward selection uses the previous available time points. But sometimes when the previous time points are also missing, it uses the median of the whole available data values. So if you impute this data with the median, of course, we have now some data which are very similar to those of other values. So assume that we have very, very small amount of data now.
Thank you.
You're welcome.